Hey guys, Miss Marusik here, and in this video we're going to be talking about Avogadro's law, an extension to what we've already talked about with that law, as well as Dalton's law. So, as a reminder, Avogadro's law states that as I add more gas into a container, if I increase the number of moles of gas, as long as the container can expand and contract, I should see an increase in the volume of that container. And you can see that in the picture here. As I increase the number of moles, the volume increased as well. And we also said that this is an equation that we can use to help us relate those variables. Remember, that's a snippet of the combined gas law where we've assumed that temperature and pressure have remained constant in both the sets of conditions. So one other thing we want to address though is that we see number of moles, and there is another equation on our formula chart that deals with number of moles, and that is that the mass over the molar mass of a substance would equal N. So to make in that substitution here, I could do that both for N1 and N2. Now here's the deal. If the identity of the gas remains consistent throughout the sets of conditions, if I have the same gas in both the initial and final sets of conditions, what that would mean is that this molar mass would also remain the same. It would also remain consistent. So if that variable remains consistent, then what that means is that we could rewrite the equation as this one down here, that V1 over M1 equals V2 over M2. So you can see that basically we've substituted in mass in place of moles. Again, this works as long as the identity of the gas stays the same. Now, where this can be really helpful is if you are trying to find the molar mass of a gas. Let's say they give you a V1, M1 set of conditions, and they ask you to find the molar mass of a gas, which basically means they're asking you to find the mass of 1 mole. As long as your set of conditions are at STP, remember standard temperature and pressure, 0 degrees Celsius in 1 atmosphere, then the helpful conversion we can use is that 1 mole, which is equal to the molar mass, is also equal to 22.4 liters, which means back up here that we could plug in 22.4 liters for our volume. Again, we can do this if we're at STP conditions. So you got to be careful in making sure you're checking for that set of conditions. All right, let's see how we can apply this in an actual problem. So looking at our first example here, it says that we have a 4-liter container, so that would be a volume, has about 10 grams of a gas, so there's our mass. That is at STP conditions. Determine an approximate value of the molar mass of this gas. Now, I'll be honest, there's other ways you could solve this problem, but one of the most helpful ways to solve this problem is by doing the formula we just looked at up above. Could you do a Pivnert situation with this where you go and solve molar mass? Absolutely, it would work just fine. However, this is kind of a shorthand way that we could do it where we can avoid using like R values and plugging in a temperature and a pressure where that would make the mental math on it much more tricky. You notice it says here to try and do this without a calculator. The reason why is that sometimes we see these problems in the multiple choice part where we don't have a calculator. And if I had to do all of that other math using mental math, it could get really complicated very quickly. So this is kind of a shorter way of doing that same type of problem. So to set us up here, I would say, hey, I have 4 liters for my initial mass of 10 grams. I'm trying to figure out how many grams, so I'm going to put X number of grams, goes along with 22.4 liters. Because I know I'm at STP conditions, and so if I'm at STP, then 1 mole, the molar mass, would be equivalent to 22.4 liters. So you can see how it kind of it enabled us to set up a ratio here versus plugging into Pivner. So it does say to try and do this without a calculator. So I'm going to show you some tricks and tips you could use to do that. First off, I always check to see if I can reduce this lovely fraction right here. I see that I have 4 over 10, so I could reduce that down to 2 over 5. And then one other thing you could potentially reduce is kind of a side-to-side reduction. If I have 2 times 22.4, that would be equivalent to 1 and 11.2. So you can see I was able to reduce it from a couple different directions here. What that did is that enables us to get 5 times 11.2, which is equal to 1 times x. So essentially, 5 times 11.2 would be equal to my number of grams that I'm trying to solve for, which is, as you can see, a lot simpler on the math than where we started at. By the way, whenever I see I have decimal values here and I'm trying to solve this with molar mass, I kind of do this in pieces. I know that 5 times 11 would be 55. I also know that 5 times 0.2 would be 1. And then I just add those pieces together, and I can see that gets me a value of 56 grams. And technically, since I'm solving a molar mass, this would be the grams for 1 mole of that substance. So I'm going to include that in my unit here. All right, here's what I want you to do. I want you to take a moment and pause this video and see if you can solve the next problem. It works in a very similar fashion. You notice it's asking you to identify your gas, but remember we can identify a gas based on its molar mass. So this next problem is just basically asking you to solve the molar mass of the gas. So take a moment, pause this video, and go try it out. All right, did you pause it? Did you go try it out? I'm going to assume that you did. So let me go ahead and put what I did up here for my work. Okay, let me scooch this up here just a little bit. All right, so I said, hey, it tells me I have a 2-liter container with about 2.5 grams of the gas. So I went ahead and set up that volume and mass ratio. And then I said, okay, it wants to know which of these gases I have. So again, I'm solving for molar mass, but they give me here that I'm at 0 degrees Celsius and 1 atmosphere. So again, that's STP conditions. So I know that that molar mass would have a volume of 22.4 liters. So then I looked to see what I could start reducing. Now, some of you might have chosen to reduce 2 over 2.5 to 1 over 1.5. And so then on your math over here, you did 1.5 times 22.4. That would get you to the exact same place that I'm going to get to. However, I went ahead and reduced the 2 and the 22.4 down to 1 and 11.2. So that got me 2.5 times 11.2. So here's where, again, I kind of broke down my math. I know that 2 times 11.2 is 22.4. And 0.5, or half of 11.2, would be 5.6. So then I just simply added those two pieces together, and that gets me my molar mass of 28 grams per mole. Looking through these options, the only one that was remotely close to 28 grams per mole would have been the N2 or the nitrogen. So hopefully that's what you got when you did it. All right, let's go ahead and look at our next gas law, which is Dalton's law of partial pressure. This law is used when you have a mixture of 2 or more gases that don't react chemically together. And I'm trying to figure out, after I've added those gases together, what the total pressure would be in a container. So let's kind of look at how this works from a molecular standpoint. If you notice down here, I have a container of hydrogen gas. I have a container of helium gas. And what I'm going to do is I'm going to add those two gases together. I'm going to combine them in this new container. So this new container has both hydrogen and it has helium mixed together. And let's notice what has happened with some of our variables. First off, you notice that pressure of the hydrogen was originally 2.4 atmospheres. Pressure of the helium was originally 6.0 atmospheres. Once I put those two pressures, those two gases, into my new container, I notice that my total pressure is now 8.4 atmospheres, which, as you can see, is the sum of those two values added together. So in order to get the total pressure in the container, all I simply had to do was add together the individual pressures. However, in order for this to work, there are some very set conditions that we have to have. If you notice up here, it says that they have to be at the same temperature and volume conditions. If we don't have that, then I can't simply add the gases this easily. You notice down here on these pictures, it mentioned that each of these containers was at the conditions of 5 liters and 20 degrees Celsius, as well as the container that I put them into. If they're not at the same set of conditions, I would have to convert them until they were at the same set of conditions, and then I would be able to add them. So we'll see some examples like that here in just a little bit. But one of the other things that I can do is relate these partial pressures to what are called mole fractions. So if we kind of look up here, it says that, hey, if I wanted to get the pressure of an individual gas, say of A within this formula, then I could get that by taking the total pressure and multiplying it by something called a mole fraction. A mole fraction is simply the moles of that substance divided by the total moles in the container. So to see how this works, we're going to actually do both a mole fraction as well as something we call a pressure fraction for helium down here. So to see this in action, I'm going to do a mole fraction for helium. And to do that, what I would do is I would take the moles that I had of helium. If you notice back up here, I had 1.25 moles of that gas. And I'm simply going to divide it by the total number of moles that were present. In this case, 1.25 plus 0.5, which would be 1.75 moles. And when I divide those in my calculator, that ends up getting a value of 0.714, which is the mole fraction of helium in this mixture final container. The hydrogen would be 1 minus the 0.714 for its mole fraction. The two mole fractions should add up to being a value of 1. Now, I also want to go ahead and calculate what's called a pressure fraction because I want to show you how these two relate. Now, there's not a symbol for pressure fraction, so I'm just going to write it out here. And the pressure fraction, and I'm going to do this again for helium, would be the pressure of helium, which was 6.0 atmospheres, divided by the total pressure of the two added together, which was, as we said, 8.4 atmospheres. And when I plug those in my calculator, what you'll end up seeing is that it too ends up equaling 0.714. It gets the same fraction. So here's something really important I want us to understand. The mole fraction, the fraction of the moles, is equivalent to the pressure fraction. We can really use that to come in handy if I'm trying to solve certain problems where maybe I have more information about pressure than I have about moles or vice versa. So having those being equal to each other is really going to come in useful when we're trying to solve math. It's also the reason why this works up here. The mole fraction is the same as the pressure fraction. So if I'm applying that fraction to the total pressure, then I should be able to get the pressure of the individual gas that I'm looking for. So let's see some problems with this in action. Our first one here gives us this lovely canister, and it says, hey, determine the partial pressure of each gas as shown in the figure below. And it gives us a note that the relative numbers of each type of gas are depicted in the figure. So we're going to set the number of molecules that we see equivalent to the number of moles. So to kind of get us going here, I first am going to address the helium. If I go count up helium in here, I see that I have 1, 2, 3, 4, 5 molecules of that. So I'm going to assume that I have 5 moles of the helium. I'm going to do the same thing for the neon. Neon, I notice I have 1, 2, 3 moles of that. And then for the argon, I have 1, 2 moles of argon. Well, if the first thing I want to do is to get myself a mole fraction, then what I would want to do is divide each of these by the number of total moles. Well, 5 plus 3 plus 2 would be 10. So I would divide each of these by the 10 moles total. And that would get me my mole fraction values. So obviously for this, divided by 10 makes it a little bit easier. 5 divided by 10 would be 0.5. 3 divided by 10 would be 0.3. And then 2 divided by 10 would be 0.2. Now, again, divided by 10, those numbers come out really easily. If they don't, you could always plug it in your calculator and get those mole fraction values. So again, these are my mole fractions here. So now it says, hey, I want to determine the partial pressure of each gas. Well, remember, I can take that mole fraction and apply it to the total pressure to get the individual pressure that I'm looking for. In this problem, it told us that the total pressure is 4 atmospheres. So what that means is I'm going to multiply each of these by 4 atmospheres. All right, so when I do that, 0.5 times 4 would get us a partial pressure of 2 atmospheres. 0.3 times 4 would get us a partial pressure of 1.2 atmospheres. And then 0.2 times 4 would get us a partial pressure of 0.8 atmospheres. So you can see I was able to get the individual pressure of each of those gases by applying my mole fraction to the total pressure of that container. All right, let's see some other examples on the next page. So this one works very similar to the one we just did. So what I want you to do is to take a moment and pause the video and see if you can try out this example for yourself. So take a moment, pause the video, try it out. Did you try it out? I'm going to guess that you did. So let me go ahead and put my work up here and you can see how your work compared. So it said here that we had 3 different gases: nitrogen gas, oxygen gas, and carbon dioxide gas. And it asked you to calculate both a mole fraction and a partial pressure. So I approached this just like I approached the previous problem, where I took my moles and divided them by the total number of moles. Conveniently here, that was 50. And that got me my mole fraction value. So each of these values that I reported here, those were those mole fraction values. I then took the mole fractions and multiplied them by the total pressure of 0.75, which you notice is a little bit less than 1 atmospheric pressure, because as they notated in the problem that we're trying to simulate high altitudes. And we know at the top of a mountain that my pressure would be less than 1 atmosphere. And so by applying those fractions to that total pressure, I was able to determine the individual pressures of each of those gases. All right, let's see some other examples here. So our next one says that we have equal masses of helium gas and argon gas, which are placed in a sealed container. What is the partial pressure of the helium gas if the total pressure in the container is 11 atmosphere? Now, this one is a little bit tricky. I'm going to give you some kind of helpful hints on solving something like this. The reason why it's tricky is it says that we have equal masses, but they haven't given me a number of moles. If I'm trying to figure out the partial pressure of the helium gas, it would be really helpful to have a mole fraction value so then I could apply it to the total of 11 ATM. But I don't have that here. And so what I'm going to do first is I'm going to think about, well, what kind of mass might I want to select in order to get these values into moles? So I could get myself a mole fraction. So to do that, I'm going to think about helium gas and argon gas, and I'm going to go get the molar mass of each of those according to the periodic table. On the periodic table, helium gas is 4 grams per mole, and argon gas is 40 grams per mole. So here's my sneaky trick for this. It just says that I have equal masses of these, but it doesn't tell me what to pick. So my sneaky way of doing this, where I'm doing it with mental math, is to pick the bigger of these two values. So I'm going to say, well, what if I had 40 grams of helium? And what if I had 40 grams of argon? What would be my mole-to-mole ratio for those? Now, there's a reason why I picked the bigger value. It's so here in a little bit, I don't end up with fractional values. I end up with some whole numbers here, and those are a lot easier to deal with. Now, as a reminder, one of the other helpful things is that the number of moles is always equal to the mass divided by the molar mass. Okay, so if these are my masses, I'm going to divide each of these by the molar mass. So I would divide this guy by 4 grams per mole. I would divide this guy by 40 grams per mole. So hopefully we can see here the reason why for argon I picked 40 grams to use here was so that this would come out to a value of 1 mole. Over here, I picked the bigger of the 2 molar masses because dividing it by something that's smaller is going to ensure that I end up with a whole number versus a fraction. So 40 divided by 4 means I have 10 moles for the helium. So 10 moles of helium versus 1 mole of argon. Well, look at what very conveniently ended up happening here for us. I have 10 moles to 1 mole, which is a grand total of 11 moles. And look what my total pressure in the container was. 11 atmospheres. So if I have a 10-to-1 ratio of the moles, I'm going to have a 10-to-1 ratio of the pressures as well. And that would give me that grand total of 11 atmospheres. So what that means here is that helium would have a partial pressure of 10 atmospheres, and argon would have a partial pressure of 1 atmosphere. I didn't really even have to apply the mole fraction because I saw that the ratio total was equivalent to the pressure total. So that made it really easy to figure out that mental math there. All right, let's see another one here. This says I have a flask containing 0.25 moles of SO2, 0.5 moles of CH4, and 0.5 moles of O2. Total pressure of the gases in the flask is 800 millimeters of mercury. What is the partial pressure of the SO2 in the flask? Well, remember, we said that to get the partial pressure of an individual gas, so to get the pressure of just SO2, that I would need to take the total pressure and multiply that by the mole fraction of SO2. So what that means is, since I already know the total pressure, I need to figure out what that mole fraction would be. So looking up here for SO2, I see that I have 0.25 moles of it. And if I add up all my moles, 0.25, 0.5, and 0.5, that would give me a grand total of 1.25 moles total. So if I'm thinking here about a mole fraction, well, let's get a little mental math here. 0.25, a quarter, into 1 1/4 is the same thing as 1 over 5, which means I have a mole fraction here of 0.2 for my value for X here. So now to finish this calculation, what I would do is I would take my 800 millimeters of mercury and multiply that by the 0.2. Now again, thinking mental math here, if I move this decimal over 1 place here, I would have to move this decimal back 1 place in order to accommodate for that. And you're thinking, why on earth would she do that? Well, that gives me 80 times 2. And as you can see, that makes that mental math a whole lot easier. And so then that would give me 160 for my value of my partial pressure. By the way, the remainder of the 800 minus the 160, which would give you about 640. If I divide that in half, since the CH4 and the O2 both were equal on the number of moles, that would give me 320 millimeters of mercury for the CH4 and 320 millimeters of mercury for the O2. So I could even figure out those other two gases pretty easily if I wanted to. All right, let's look at our next one here. This one says, hey, when I have 4 liters of helium gas, 6 liters of nitrogen gas, and 10 liters of argon, each is 0 degrees Celsius in 1 atmosphere. They're pumped into an 8-liter rigid container. What is the final pressure of the container at 0 degrees Celsius? Now, a couple quick things here. I notice the temperature is remaining consistent, so that's good, okay? If each of these were 1 atmosphere, you might be tempted to say, well, hey, if they're each 1 atmosphere, then I just add them up to get the total, right? Well, as you can see here, 3 atmospheres is not an option. Here's the reason why. All of these are at different volume conditions. And so obviously that's a problem. I need to add these up when both temperature and volume conditions are the same. So what we're going to have to do here is we're going to have to figure out for each of these at 1 atmosphere, if I put them into the 8-liter container, how would their pressures change? And then once I get those new pressures, then I can simply add them up together. So to start us off here, I'm going to first talk about the helium. Okay, now let's think about this. If I have an initial volume and an initial pressure, and I'm trying to figure out the new pressure at this new volume, hopefully we can see that we would be using Boyle's law here. Okay, and so what I'm going to do is I'm going to calculate, hey, if I had 1 atmosphere for 4 liters, what would that new pressure be when I change the volume to 8 liters. Okay, so to get P by itself, I would divide by 8. 4 divided by 8 is 1/2. So that would give me 0.5 atmospheres for the pressure of the helium. Now I'm going to do that same process for the other gases. So for N2, again, I would have 1 atmosphere of pressure. This one was starting off at 6 liters. I'm going to figure out the new pressure at 8 liters. All right, so 6 divided by 8 would be the same thing as 3/4, which would be 0.75 atmospheres for the pressure of the N2. All right, last but not least here, we have our argon. Argon, again, starting at 1 atmospheres when it's at 10 liters, but now I want to figure out the new pressure when I'm at 8 liters. 10 divided by 8 would be 1.25 for that pressure of the argon. So now if I wanted to get the total pressure, now that I have the pressure at that 8-liter condition, now I can simply just add these up. 1.25 plus 0.75 would be 2. Adding another 0.5 onto it would give me a grand total here of 2.5 atmospheres. All right, we've got one more here, and this is something that you would probably see, say, in the free response part of an AP test. Okay, it says consider the flasks in the following diagram. What are the final partial pressures of H2 and N2 after the stopcock, which is this valve between the 2 flasks, is open, and what would the total pressure be in torr? So here's the deal. They are saying that, hey, right now this is closed. And with it closed, this side of the container is 2 liters and 475 torrs of H2. This side of the container is 1 liter and 2.0 atmospheres for the N2. And what we're going to do is we're going to open this valve. Now let's think about what would happen to volume when I open this valve. When I open it, the 2 liters and the 1 liter are going to combine. And that means that I would have a new total volume of 3 liters. Now, that's going to help us get our partial pressures here in just a minute. But let's go ahead and think about our total pressure. Our total pressure would be equal to the pressure of the hydrogen gas added to the pressure of the nitrogen gas. However, again, I can't do that with the pressures as they are for a couple reasons, one of them being they're in different units, so we'll have to address that, but also because these were not recorded at the same volume conditions. I'm going to have to figure out what those new pressures are of each of these at that total new volume of 3 liters, and then I'll be able to add them together. So let's go through that process here. So let's start off with the H2. And again, they didn't mention temperature here in any sense, so I'm going to assume that that remained constant. So that means I'm going to use, again, a variant of Boyle's law, P1V1 equals P2V2. Obviously, if temperature did change in the conditions, I could also include divided by T on both of these as well. So you could do that just as easily, you just need a little more work, okay? What I'm going to do is I'm going to set the P1 and V1 as my initial set of conditions, and my second set of conditions is going to be my new total stuff that I'm looking for. All right, so my P1 here was 475 torr. My V1 was 2 liters. My P2 is what I'm looking for. So I'm going to put pressure of hydrogen gas, the volume of 3 liters. All right, so I would divide that 3 liters over, solve for the pressure of the hydrogen, and that gets me 317 torr once I plug that in my calculator. So that would again be the pressure of the H2 at the new set of conditions. All right, I would now do the same thing for the N2 using the same equation since I have the same variables. So here I was starting off at 2 atmospheres. And we'll address that unit here in just a little bit. I had 1 liter. And I want to figure out what the new pressure would be of the nitrogen at my 3 liters. All right. So again, I would plug all that in my calculator and see what I would get for that pressure. That gets a value of 0.0667 atmospheres. And so that would be the pressure of the N2. Now, obviously, that's an issue because that unit doesn't match. So I would need to do a quick conversion of it. 0.0667 atmospheres. And we would say that, hey, for every 1 atmosphere, that would be 760 torr. So we could do just a quick dimensional analysis, and that gets us a value of 50.7 torr. So then, to address the question, these would be my 2 final partial pressures of H2 and of N2 after that valve has been opened. To get my final total pressure, I would want to add these 2 together. 317 plus the 50.7. By the way, on both of those, I had originally kept 3 sig figs because my initial values had 3 sig figs. Here, when I'm adding, I would want to do the least number of places past the decimal. And so when I do that, I would keep no places past the decimal. So my new total pressure would end up being 368 torr. So again, that is our P total once I add those together after opening that valve. All right, hopefully we're starting to feel confident with working problems with both Avogadro's law, kind of in a different way than we've done previously, as well as with Dalton's law. If you have any questions or need any help, please feel free to email me. Bye, guys.